Okay, well, I want to kind of talk about the relationship between research into neurobiology and what we learn about brains and how we design hardware and software for modern machine learning. Now, of course, these are enormous topics, and I can't touch on everything. So I'm going to give you, a little bit that's related to my work, okay? And there are endless rivers and seas of other information and stuff, but I'll try to kind of keep it, my kind of little view of this enormous world of research. Um, so so here's an image, okay, and hopefully all of you can see it. And it turns out that you can tell in about 100th of a second that this is Mount Fuji. These are experiments done at MIT. 100th of a second, okay, to know that this is Mount Fuji. And you're doing this with your brain, right? And you're doing it with your brain using these neurons, and in 100th of a second, maybe, I don't know, several few 10, 5 neurons fired. That's it, no more. And then you can still in that very short amount of time know, right, what's going on. And how does that happen? Well, it turns out that our brains, right, are a very efficient you know neural computing machine. The basic building block, right, of our brains are these neurons. Okay, and what a neuron is a cell, right, that has an input area called a dendrite and an output area called an axon, axonal arbor, if you will, and um, and the kind of this kind of axon is covered with kind of other cells that kind of insulate it. So you've got this kind of way of sending information across from the input area, if you can see my cursor, to the output area. And this process, this cell receives inputs, chemical inputs along these connections called synapses from other neurons, okay, and outputs, information through synapses to other neurons. The computation is essentially, okay, I get the signals from the synapses, then I accumulate them. This is kind of an electrical pulse. Then I sum it up in some way, which to this day we don't know exactly what the exact function is. And then if I pass some threshold, typically I send a signal, an electrical pulse, down the axon, which is then spread through along the axonal arbors to the synapses that connect to other neurons and so on. Okay, so this is kind of how, in a very rough way, a neuron functions. Now, connectomics, the field that I do research in, tries to map the connectivity of neural tissue at the level of these synapses. So a synapse, all these little things that I showed you that connect one neuron to the next, it's essentially, here's an axon with and this is kind of the synaptic connection. And what happens is that you have these pouches, okay, full with neurotransmitter, chemical, and when a pulse comes down the axon, it causes these pouches, these vesicles, to open, and they release neurotransmitter that kind of very quickly is absorbed by receptors on the other dendritic side of another axon, another neuron, and that kind of chemical transfer of the neurotransmitters is a signal that causes then the next neuron to start to develop, this kind of electrical current and move the next, send a message to the next one. So this is what a synapse looks like. So kind of think of it as, these cells are sending a, electric signal, then chemical, then electric, chemical, and so on. Of course, it's all chemistry, but has to do with the different changes in ions. But we won't get into that. So that's kind of how it works, of course, and it works on a very interesting scale, on a very small scale. But the thing when we think about when we think about brains, right, we don't think about individual neurons. We think about processes like like vision, like planning, like balance, right? We do really big, complex things, right? And and so the question is, okay, so this kind of thing is what brains do, right? Um, and why has it been so hard for us to understand how, a brain that we have in our hand, how does it actually do it? Why is it so hard to understand that? And, there are a bunch of reasons why, right? This is complex. Um, but one of them is just the scale of things. Okay. And when I say the scale of things, I want to give you an understanding of what we're talking about here. So, if you look at this brain, this is a human brain, right? Um, you know, this is kind of the front of this is where your eyes are, and this is the back of your head, right? Um, and the scale here is about 10 centimeters. Now, if I try to take a region, right, that is a kind of a tenth of this, okay, 1 centimeter, and I want to look at it, expand that region, okay, so I'll take that 1 centimeter, and I'll take a look at what it looks like. Then what I have, right, are these two kind of distinct regions, gray matter and white matter, which some of you have probably heard of, right? And so in the gray matter, let's understand what's in the gray matter and let's understand what's in the white matter, okay? So let me go down another factor of 10. So here's another little piece of brain, another factor of 10 smaller. So now we're looking, right, at 1 millimeter, okay? So 1 millimeter of brain, okay? What do we see in there? Well, what we can see here is, a pyramidal neuron, okay? And in this neuron, right, this is like a neuron in cortex, okay? And what you see are these are the dendritic trees, one area of the basal area of the dendritic tree, and another area of the dendritic tree. All of these are receptors, right? And then you can see an axon that is going across the white matter to somewhere else in the brain, okay? But let's keep going. Now, okay, let's take another factor of 10 smaller area, okay, and expand it. Okay, so now we're looking at 100 nanometer. Okay, so what do we see here? Well, what we see here is, this is a dendritic arbor, okay, and along the dendritic arbor are these little dendritic spines, okay, and each spine is going to actually be part of a synapse, okay, those connections that I talked about before. So let me go and let's expand again and take a look at something that is just 10 nanometers, okay? Okay, so what do we see here? Okay, actually these are microns, not nanometers, because this whole thing would be probably 30 nanometers each one of these little things. But anyway, so I'm 10x smaller, and what you see here is a view of one of these little kind of arbors. Here it is. Okay, this is an image from an electron microscope. At this level, we can only look at things with an electron microscope. So what do we see here? We see, this is the kind of dendritic spine that I talked about. This is the axon terminal. Okay, this is the axon terminal, and in it you can see the vesicles, right? And this is the synaptic connection between them. And what's happening here, right? When I said that these little vesicles will open up and send a signal down here. That's essentially how the axon and the dendrite of these two neurons will talk to each other. Okay? So if you want to understand why it's difficult, right, to kind of understand brains at that kind of operational level, okay, it's because if you think about the, you know, the resolution of, let's say, a voxel in MRI, right? People take these beautiful images of brains where you see the kind of, which regions are highlighting when I'm thinking about, my favorite movie star and so on. That's at the level of a cubic millimeter, okay? And, you know, this is about 10,000 trillion times larger, okay, than the voxels of the electron microscopy that I'm looking at here, okay? So the resolution here that I need to get this right, and the resolution in which I'm talking is so much smaller, makes it very, very hard to argue about these things and understand them. Okay. Um, so great. So you know, neurons are it's not mapping neurons, right? Like I said in connectomics, was done with light microscopes long before we had electron microscopes. In fact, it was done in the 19th century, okay, and the beginning of the 20th century. A guy called Camillo Golgi invented a technique that painted neurons, okay, this kind of silver nitrate technique, okay, and the Golgi technique allowed another great scientist, Santiago Ramon y Cajal, to actually map neurons, okay, and draw accurate kind of, their accurate shapes, okay, and Cajal looked at these neurons through with the Golgi technique that he painted with a light microscope, and he drew amazing pictures, okay, and he came up with a theory. At the time, before Cajal, Golgi and others thought that the brain was one big connected cell, okay, and Cajal, just by looking at light microscopy images, okay, came up with the idea, okay, that actually the neurons are separate cells and each one is firing down the axon to another cell. This whole thing without ever actually seeing the firing and without actually ever seeing a synapse, because you couldn't see a synapse because you can't see them without an electron microscope, okay? In fact, what happened was that Golgi and others just did not believe Cajal, okay? And but together they won. Actually, they won the Nobel Prize in 1901, I think. And in his Nobel Prize speech, Golgi spent the whole speech explaining why Cajal was wrong, which of course Cajal was right. And in the 1950s, with the invention of electron microscopes, one could actually see synapses, and Cajal was proven right. Okay. So the issue, though, with these images that Cajal drew using the Golgi technique is that they are very, very sparse. You can't really see all the neurons that are in the area. This technique of coloring neurons, of staining them, was very limited, and so you didn't really see what totally was going on. And so this is where modern connectomics comes in, okay? And with modern connectomics, what we are trying to do, okay, is actually take little slivers of brain, okay, and put them under an electron microscope. The way this works is as follows. I take a piece of, let's say, mouse brain tissue, and I embed it in a resin, and I put it on what's called a microtome. I'll show you this in a second. This is this device here, and there's a diamond blade here, and the piece of resin, is going to sit here, and I'm going to take this microtome, and it's going to go up and down, and slices of the brain are going to float over a bed of water onto a tape. Okay, so you're going to get the brain on tape, essentially, slice after slice after slice of brain on tape. Okay, and this is my colleague Jeff Lichtman from Harvard. This is this is not intended to show you how small Jeff is, but how big the microscope is. This is a 61 beam microscope that is used to actually kind of look at these images. And so here are slices of brain, okay, on a disc. Each one of these guys here, right? A lot of little tiny slices on a essentially a piece of plastic, right? And if I look at one of these pieces that we've sliced, okay, it looks something like this. This is about a millimeter. Okay, this thing is about a millimeter. This is pretty much, if you just looked at it, this is what it would look like with a light microscope. But if you went in deeper, you could see a lot more. And so what we're going to do is we're going to take these slices. Here's an example of 10,000 slices, 10,000 sections. Okay, I'm going to take these 10,000 sections, and I'm going to try to render them together with computer techniques into something that we can understand. Okay, and so this is about 100 terabytes. And if I look them all together, I would have a block of a piece of the thalamus of a mouse. Okay, just so you get an idea, this is a penny, and this is what this piece looks like. Okay, so it's like a grain of salt. Okay, we've taken this grain of salt, and we take a grain of salt and we cut it 10,000 times. Okay, now what you get are those images that you saw. Essentially, each one of these is a slice through a neuron. Okay, and what we'd like to do is kind of reconstruct it. You can see that actually this looks very dense, right? There's a lot of neurons here. Okay, but what we want to do is use machine learning techniques, okay, to actually be able to see through this. So if we take a block like this is a much smaller block, okay, and we take the slices and we use a machine learning algorithm to actually identify the neuron through the slices, then we can go and reconstruct, the whole thing, the neuron, the synapses and everything, okay? So from the slices to these neurons, okay? And we do that with machine learning. So maybe we want to use what we understand about brains, about machine learning, but the first thing we do is use machine learning to kind of understand brains. And so, for example, we have techniques for tracking, a neurite through this volume. So what you're going to see here is a video of how, we track with machine learning, we identify the boundaries of the borders of the neurons, and we can track a single very, very tiny neurite through the volume. Okay, so you're seeing the view of the machine learning algorithm as it goes slice after slice through this, identifying all the time, keeping track of where that neurite is. Okay. And what we get when we're done with this, right, when we actually manage to do this tracking, is the ability to reconstruct, pieces of brain in a dense way, not the way Cajal and Golgi did, where every region I had a few neurons, but rather, really, what does it look like? So if I look, for example, at a piece of brain, and I look at these dendrites, right, with all these little, these kind of areas where synapses are going to connect, right? So what am I going to see? Well, here are two dendrites, right? And these are all the other dendrites in the same kind of volume right around them, okay? These are all the other dendrites that go through that piece of, volume of brain. And these are all the axons that go through that piece of brain. And these are all the glia cells, the support cells in that area. And And the actual tissue is the combination of all of these. So it looks extremely dense. Okay? So that's what I want you to understand. It looks really dense because it's really interleaving a lot here. It's very efficient. Okay? So, and this is only, right? This is only 100,000th of the 100 terabyte grain of salt that I showed you. Okay? So if you will, right, our brains are, enormous machines, okay? And when we think of them, we think, oh my God, that's so much compute. There's so much stuff going on there. How are we ever going to do that with computers? Okay. So I want to take the next leap in this talk, and I want to go and talk about actually, what can we learn about the relationship between brains, physical brains, physical neuron brains, and, modern machine learning. So, the basis, many of you probably know, of how we do modern machine learning, right, is to use devices which we call GPUs or TPUs, right, and so on, right? And there are more than 70 startups building different types of hardware for machine learning. It's changing all the time, okay? The idea is that to do machine learning, we've got to have throughput computing, right? We've got to have hardware that will allow us to do an enormous amount of operations like the brain, and all of that in parallel. So I have a lot of throughput. Okay. Your typical GPU, thousands of cores, and connected with high bandwidth memory. Typically, if this is your GPU that you have access to, it's probably 16 to 32 gigs. If you're richer, you can get an 80 gig one, right? You put your model and your data into your GPU memory, and then you have, 10 teraops of compute, 100 teraops of compute applied to it, okay? So that's how we compute. And then if we want to do something much more meaningful, like train a very large model or do something like that, right? Or, then the way we're going to do that is by connecting these devices together to make these huge pods, okay? So let's examine what's going on here. So we are building these machines and we are using them. But the question is to ask ourselves, okay, is this really the right model? Okay. And what can we learn from brains about it? Even if this is what we're going to do, what can we learn from what we know in neurobiology about this path? So the human cortex, right, has about 16 billion neurons. Okay. A neuron spikes about 0.16 times per second. Each neuron in an adult has about 7,000 synapses, okay? But, it's not like the synapses are, every synapse, every two neurons are connected just by one synapse. Here you can see an example of, what you see here is a kind of an axon connecting to the dendrite of some other neuron, and you can see that there are 5 different places where this axon is connecting to the dendrite. So kind of if I want to do this calculation and I have 7,000 synapses, it's not like I'm going to connect to 7,000 other neurons, okay? Probably 700 or 70 in some cases, okay? So let's just say 700, okay? Let's say it's 700. So, okay, so 16 billion neurons, each fires every 0.16 of a second, 0.16 times per second, times 700, connections is about 2 trillion operations per second. So if I think about, a brain in terms of in the same terms that I think about neural networks, I have a weight and I multiply it and I get a result. right, then I have about 2 trillion operations per second happening in our brain. Okay? An iPhone does 5 trillion. Okay? So I don't need, my brain is not more powerful than an iPhone. Okay? It's not this monstrous machine. It's not a TPU pod. Okay? Cortex is 5 to 6 orders of magnitude less compute than this TPU pod. And I want you to keep that in mind. So if you want to mimic us, okay, you don't need that much compute. What about like image recognition, right? I want to recognize an image, like the typical thing, a 224 by 224 image, right? About 0.05 million pixels, right? It takes about 20 to 30 billion operations to do that on a popular ResNet or whatever, UNet that you would use. Okay, the human iris has about 100 million pixels. That's 2000x more pixels, right? And a neural network would take, with this, about 40 trillion ops per image. So if you want to think about it, we can, we recognize an image in about, 13 milliseconds or less, okay? So even if the whole cortex was used for this, okay, that's 2 trillion times 0.13, about 20 billion operations per second. Okay? So if you think about it, right, the brain is 3 to 4 orders of magnitude more efficient in processing images, right, than the neural networks that we're using right now. Okay? What about memory size? Okay? In terms of memory size, if you think about, if you think about the human cortex, there are about 300 trillion synapses, okay, in your cortex. So what's the size of that graph? If I wanted to represent it in the leanest way, without really anything but, some weights, okay, and connections, it's about 1.2 petabytes. So to represent it, just to store it without any kind of complexity would be, about a petabyte, right? Your typical GPU, okay, has about 32 gigabytes of HBM, high bandwidth memory. Okay, so even a desktop, by the way, your desktop could have 1.4 terabytes. Okay, but your GPU has like 30 gigs. Okay, so your GPU TPU pod, right, is about 3 or 4 orders of magnitude too small. Okay, to kind of hold your brain. Your brain is, if you want it to hold brains and run them, it's just going to be too big for it. So to summarize this whole thing, my rant here, right? A GPU, right, is thousands of cores, right? With, thousands of cores, right? With, gigabytes, a few gigabytes of memory, like an iPhone, right? So if you will, I've got a teraflop of I'm aiming at a teraflop of compute, right? With the phone, the memory of an iPhone, where what I really want, right? What I need to mimic a brain is probably an iPhone of compute, right? On a petabyte of memory. It's kind of, we're building the opposite thing of what we really need. Okay? We don't need all those flops. What we need is memory, right? And the right algorithms. Okay? So not knowing the algorithm, we don't know how nature does it. And because of that, right, we're stuck with these massive computations right now. So given this, what is the future of neural hardware software? Okay? Well, one thing we have to understand is this, that our hardware doesn't have to imitate, right, brains. I mean, in terms of of parallelism. The reason that your brain is parallel and needs to do like a, like let's say you want to do 1 billion operations per second, okay, and you're doing it with neurons. Then you need 1,000 or a billion. Sorry, you want to do 1 billion operations per second. You need 1 billion neurons to fire every time. Okay, if you wanted to do 1 billion operations per second. Okay, but in a modern processor, right? You know, um, in a modern processor, you can do 1 billion operations sequentially. You know, a typical desktop will do more than 10 billion instructions per second. Okay, so it's not we don't need the parallelism. Okay, what we need to learn from neural tissue are two things. One is that even though it looks very dense in the volume, it's actually very sparse in the computation. Okay, and it has locality of reference. Okay, when a neuron fires, its synapse fires into the neuron right next to it. Okay, and right next to it, and right next to it, and so on and so forth. So really, everything I'm doing is very, very localized. So I'm saving the energy by being local in some sense. Okay, and I'm getting speed because I'm local. So these kinds of things are really critical. So the question is, can we mimic this? Not so much the flops and flops and flops that we think we need, but rather the sparsity in the locality of reference. Okay? So we need to understand the algorithms for that. We don't understand them yet, right? So today, what we're trying to do is improve GPU and CPU performance with software algorithms that are based on sparsity and on caching. Sparsity, like the brain, caching like the locality of reference of the brain. And tomorrow, hopefully, we can build in hardware, some kind of sparse prefetched brain that will execute all in hardware. Okay? But today, what is it that we try to do today? Well, here's an example of what we try to do. We have two types of machines that we use for computation. Okay? We have CPUs and we have GPUs. If you look at the CPU, you look at the GPUs, right? They have thousands of cores, right? Each one with a very tiny cache, and I'm sorry about that. The very tiny cache, and they, and they have a lot of bandwidth to memory. Okay, they execute synchronously, layer after layer after layer. So they read, from the memory and write, and read from the memory a layer and write, and so on and so forth. So they're executing synchronously layer by layer. And this works pretty well for a GPU. If we try to do that on a CPU, okay, right, run layer by layer, CPUs have very large, very few cores, but they have very large caches, okay? So I don't have that much compute, right? So if I try to do this layer by layer, and they have very limited bandwidth to memory. So this works very poorly if I try to run things in a CPU like this, okay? So what we can do to run fast on CPUs, right, is to take, we can take a neural network and we can pass it through a process which we call pruning. This is just like what happens in brains also. When you are very young, when you're born, you have, probably, twice as many neurons as you have now, okay? And so, and twice as many synapses. Sorry, more importantly, you have twice as many synapses. And we prune them, okay? We're cutting them down over, the period from when you're about 3 years old and onward. You're just kind of all the time cutting these connections. And so, we can do the same thing for neural networks, and it turns out that we can do that while preserving accuracy. And we can also run the neural networks, okay, differently than on the GPUs. We can run them utilizing the large caches. We can actually run the network depth-wise in the caches, okay? And so we can execute them asynchronously, depth-wise in cache. So prune them and execute them depth-wise asynchronously in cache. And what you get from that, okay, if you do that, you can actually make the CPUs perform in terms of latency just like the CPUs. Okay, this is not a generative AI example. This is not generating things, but actually just a BERT model, okay, a very basic kind of language model. And what you can see is that a 4-core CPU in terms of latency is as good as any of the GPUs if you use sparsity and you run things using the caches correctly. If you kind of mimic the brain, okay, being sparse and running with locality. And this is true also for throughput. You can actually get a lot of throughput from a CPU by doing this, okay? So that's what you can do for CPUs using sparsity and caching to get them to, to perform well. But of course, the world is moving forward. And today, everybody's interested in new generative models that are getting bigger and bigger and bigger. Okay? And so what do we do there? So again, now, GPUs have a real problem. If we want to deal with these large models with GPUs, then the problem that we have is that we've built these devices to have more and more and more flops. You can see here over the last generations of hardware that NVIDIA has generated, from the Pascal GPUs, the Voltas, the Turings, the Amperes, and now the Hoppers, right? We've managed to get the flops up by a crazy factor, okay? But the memory is pretty much stable, right? I went from 16 to 80 gigs in terms of the size of my memory. And just so we understand, your desktop, okay, can have a terabyte of memory. So we're really, GPUs are lagging behind in terms of memory size. Okay? But again, here we can use sparsity and we can use caching to make them work well. And in fact, there's an incredible increase now in research, okay, on sparsity, because we're understanding that we really have to mimic the brain here. We can't avoid understanding those things that nature has understood from before. And what will the future, the near future look like? So this is not, the very far future of a brain-like computing device, and not the current day, okay? Or this is maybe the day in the coming years. Well, what we're going to see are, are kind of devices that are combination of CPUs and GPUs. This is an example. This is an image of the Grace Hopper chip from NVIDIA. This is the H200. It's going to come out into the marketplace in the next, months, right? And what it is a CPU plus a GPU that also offers you ways to do sparsity, combining sparsity to make the models smaller together with running on a device that has both a CPU with a lot of memory and a GPU with a lot of compute is probably where we're going to be in the near future. And I think with that, I'm going to finish.
1 second here, everyone. Yasher Koach Nir for your extremely insightful presentation. Can I get a virtual round of applause, everyone in the audience, please? Thank you so much. And so now, what questions do the audience members have, and we can answer your questions.
So Manak from Nokia asks, how might one check if dense reconstruction of neurons from slices has been done correctly?
So the way we do that is by having neurobiologists go and create ground truth test examples, right, and check everything. So one of the biggest problems that we have today in connectomics is that after we've generated a volume like this, we still need to do a lot of checking by the neurobiologists. This is an open problem that we're trying to solve with better machine learning algorithms.
Amazing. And then we have another question from Karun asking, is there a proof that only a few neurons are fired for recalling Mount Fuji?
No, I don't think anybody has measured this number, but I think there are enough data sets that you could measure it if you want to. The typical rate at which neurons fire, right, when they look at images is known. In fact, I have data sets like that. I don't think it's very different from what I showed. So you can compute it. I don't think anybody's really tried. Definitely not with Mount Fuji.
Amazing. And then we have another question from Jim asking, can you comment on the similarity or differences between the regular connectivity of pods and the structure of brain connectivity? Is it always pruning or is there new growth as well?
I'm not sure I understand the question. Can you repeat the question again? Let me try to parse it again.
Yeah, of course. Can you comment on the similarity or differences between the regular connectivity of pods and the structure of brain connectivity?
Oh, the regular, as in the pods are connected in a regular way, and brains are not. So here's the thing. I don't think that is the key. Just my intuition. That's not the key element that is going to differentiate them. I mean this in the following sense. The brain looks pretty regular when you look at white matter and how like axons go across the brain from one region to the next, okay, in bundles. They just don't, it's not like every axon goes randomly somewhere, okay? They actually go in bundles, okay? And so there is quite a bit of structure to how things are connected. It is not, being built by nature. Okay, there is, of course, an amount of randomness there, but there is also a lot of structure and a lot of modularity. Okay, so I would not say that they are that different. It's just that when we humans engineer things, it's much easier for us to produce them in a very, very modular type form.
Fascinating. And then we have a follow-up or a similar question, I guess, asking on your insights on other compression techniques like quantization and clustering of weights and how they actually relate to a biological brain with things like sparsity and pruning.
So, to my mind, in my research, I find that sparsity and quantization are very closely related. I do not think that you can separate them that easily. They both are reducing, the overall size of your representation. And by doing that, they are causing you to lose parts of your representation. Okay? And sparsity is at high levels of sparsity is more damaging to your representation, and you need to do a lot more retraining to regain accuracy. But similar things happen with quantization, and my belief is that as we go forward, we will see that they are tightly related to one another. What was the other part of the question?
Just generally insights on other compression techniques.
So I think, the other thing that I would call a compression technique is distillation. I would say that that's another way in which we do this kind of reduction in model size. In the end, if you want to think about what a neural network really is, whatever size the network is, it's really a representation, a compressed representation of something, that if I had enough neurons, I would expand it so that I had enough neurons as I have dimensionality in my problem domain, then I would have a neuron per feature. Okay, but I can't do that. So as I bring things down, as I kind of come down in the size of the network, more and more features are being represented by these neurons. And so it becomes harder and harder to make this thing accurate. And that's what's really happening here. And so methods like distillation help me in getting smaller models. That's another way to do that. Okay, so sparsity, quantization, distillation, all of these things used together are going to get us, to the right place, if you will.
Amazing. And then we had just one comment. Jim was saying that, as they used to say at Sun Microsystems, the network is the computer. And his thoughts are that we need a better one that evolves with the training network. Any
I love
comments
that.
there? Yeah.
I love that. I think that's completely correct.
And just like a general question, where do you feel that research is headed?
I think you have to separate right now hardware from software because they're not moving together, unfortunately. I think software is now finally understanding that we have to have, so what happened with generative models is that now, okay, the world is kind of split into two. If I'm an individual running this on my computer, then I basically am doing vector times matrix multiplication to do a generative model. And if I'm running in a data center, I'm doing matrix because I'm batching things together. So these types of computation have split, okay? And now I need two types of software for them. Software that does this massive kind of gathering of compute so I can use the GPU compute power that I bought for a lot of money. And then on the desktop, right, I need to find ways of using the fact that I don't have a lot of compute because all I'm doing is a vector matrix multiply, but everything is slow because I have less bandwidth. So everything is going to be games around reducing the memory size, the bandwidth, and improving the caching of things. And that's what we're going to see playing in hardware and in software.
Amazing. And then we have another question from Karun asking, is multi-layer feed-forward model versus content addressable recall applicable in certain applications? For example, logical reasoning versus image recognition versus language understanding. And how would you prioritize, I guess?
I think what we're going to see is that large collections, large networks of neurons trained on data can do all of these things in a way that makes them not separable. I don't think you need a different network for computer vision than you need one for language, than you need for anything else. I think this is all going to converge. I think it's about size and how we train, and we have to just learn how to do that.
And with that, it feels like we're moving towards that with the recent developments and multimodal models coming out. Or do you feel like that's still many, many years out?
Yeah, I don't want to get into this, how far out it is. But I will say that in my little world, right, of making things work better and faster, there is a lot of work to do to enable, the kind of growth that we want to achieve. And and we're not even in all this talk, I haven't even really, I've talked just about silicon versus brains, but there's a lot of science happening now at building computing devices that are not necessarily VLSI chips. Okay, we can shrink things by many orders of magnitude by computing chemically, molecularly. These are the paths that you will see computing going down to, right? And we have no idea what they will look like, but that's where we're heading. Because if you want to run something that is as smart as you in your Apple Watch, we've got a lot of work to do. It's not going to be silicon, okay? So, and in fact, the whole idea that you're going to wear it on your hand is ridiculous because we'll genetically modify it into your brain behind your ear. So there's a lot of way into the future with this, okay? And we're at the very, very beginning of this story, but it's fascinating. It's fascinating. We have to solve today's problems, but science is working already on, 1,000 years from now.
Wow, awesome. And again, everybody, thank you to our speaker
Thank you
here,
guys
Nir,
for
for
having
coming.
me. Yeah,
Yeah, we
absolutely.
sincerely appreciate it. If we could have a little
Let me just
round
wrap
of
things up,
applause.
and then
Probably going to wrap things up so we
let's
can
get
be
a
mindful of
round of
this
applause,
time.
everyone. Okay. So thank you so much, Nir, for taking your extremely valuable time to educate us students. I'll be following up with you shortly to inquire where we can send you our drive of chocolates. And then we'd like to extend our deep appreciation for your time and your willingness to speak with us. Thanks to everyone else in the audience for your attendance. And we'll see everyone here next Wednesday. We're going to have Jeff Ullman.
Take care, everybody.
Bye,
Bye-bye.
guys. Thank you.
Bye.
Thank you for joining. Bye-bye.
Bye, everyone.